All right, and now we are ready to start. So welcome back, everybody. Today we are going to start with this first lecture on discrete planning. So if you remember last lecture, we were just defining what planning is in the context of this course, right? So this definition is very broad, and we were giving like those definitions that are more relevant for us. Remember, it's mostly focused on AI, robotics, controls, these kind of things. And at the end, planning is just getting from initial state to final state, right? So today we'll start with what I think is the most reasonable approach to planning, right? Discretization. It has a lot of applications. The most common approach, and I'm sure that many of you have already seen like this applied maybe in other domains or well applied to other problems. Okay, so the idea is very simple. What we have is we need to create a planning problem, and we will transform it into a graph search problem, right? So this that looks like a straightforward approach, it might not be so, depending on the state space, depending on actions, depending on many things, right? But at the end, the idea will be this. So if we are able to transform our planning problem into a graph search, then we just use a graph search graph search techniques that are out there for you to just apply. Okay, I think I have a little problem with cursor here. Okay, I think I'm gonna forget about this. Okay, so on this first approach, we will study only discrete spaces. So why is that, right? I already gave like some hints, but another good motivation is that there's many examples that consider discrete problems, right? So it's not just that you discretize the space. No, there's other problems that by definition are discrete, right? So this is kind of place where we'll be taking advantage. So some problems are discrete, others you can discretize. So that probably means that discrete planning is a very popular approach, right? So I think it's a very powerful tool, and we should know about this. And of course, at the end of the class, I will know a little bit more. The objective is to find a feasible solution. So remember what feasible means. It's just finding a plan if there exists one. Luckily, from the algorithmic foundations, all these algorithms on graph search guarantee that if there's a solution, if there's a plan, we'll find it in finite time. So this is a great guarantee that all this discrete planning is built upon. The only negative side is that, well, we'll have course of dimensionality, right? So I'm sure that this problem has arisen in many other domains. So the moment you start having, you need a discretization of your space, and you have many dimensions, course of dimensionality is just going to appear. It might appear having like high computational time. It might appear requiring you to have like immense amount of memory. There's many manifestations of course of dimensionality, but at the end, all of them are bad, right? So what is the kind of solution or heuristic that is applied here, right? So we'll see today that still, even though that course of dimensionality is really an issue, we can speed up our search by a lot if we apply some heuristics, right? So this is, remember, this is kind of first lecture on planning. Don't worry if I say heuristics, because in practice, they turn out to be to work very well, right? So we'll see some of them. We'll see some of their limitations also. But I think the debate is open because on the one hand, these techniques are very powerful. They are complete, right? So you will find a solution. On the other hand, well, course of dimensionality is going to appear, right? So I think this is kind of a dilemma for all of you later if you want to apply this method. Let's start with some examples. right? First example that is very, very typical is traversing a graph. So we have here, in this case, this undirected graph, but it could be directed, doesn't matter much. And then this is just a direct example of graph search, right? In this case, what we want to create is this structure, right? So we already have the graph structure created for us. And then we'll just be applying graph search algorithms to traverse the graph, right? So maybe what we look is just a solution from an initial point to final point, right? But maybe we are looking for other things, right? So second example, let me see if I can, oh, okay. Second example is a little more interesting. So why? Because we don't really have a graph here, right? What we have is simply a grid space that has a lot of positions. Some of them could be your cells, like for instance, this is an empty cell. And for instance, here we could have obstacle, right? And we could call this like obstacle cell, something that is not traversable, something that our state variable is not possible to have, right? So we can actually convert this problem into a graph following a very simple strategy, right? Imagine that we are here at any position, like for instance here. So what we can create is a simple connectivity graphs depending on the actions that are applied here. In this case, we know intuitively that there's like 3 possible actions. This one, by the way, is not possible because this results in obstacle, right? So if this state is an obstacle, then we cannot really apply this action because this results in a state that is not inside the set of state variables, right? So we'll have 3 actions here, going up, going down, going to the left. With this, actually what we can do is convert this maze into a graph, right? So imagine you do this many times, you have exhaustively calculated or what are the actions at each state variable, right? So for each state variable, you know what is the action you can apply. So for instance, you can only go up on this. We have this, and then we'll see that the problem is just going to be like how to traverse this graph. The thing here that is very subtle, and this is why discrete planning is not exactly graph search, is because we don't know the graph a priori, right? We just have like this representation that is this grid map or whatever it is, right? And the algorithm, what is going to allow us to do is to create this graph as we are traversing it, right? So while we are calculating a solution, we'll see that we can create like a graph, right? It's going to be a tree, but well. Okay, so we'll see more examples later. I think this is the canonical example. But there's other more complicated examples, right? For instance, this is also called like a discrete planning problem, very, very popular one, which is called logic-based planning. Imagine here what you have is your pen consists of many, many pieces, and you need to put them together, right? So how to assemble a pen? This is really complicated thing, right? If we start with no information, literally we could be connecting any part to any other part, right? So you try just to put them together, some of them work, others doesn't work, right? So if we just analyze the state space, the possible state space is gigantic, right? So usually this is known also as combinatorial problem. We know that there's ways for pruning, like all this search, right? So there's no need to, I don't know, study if this thing connects to, oh, yeah, this is very bad because I don't have pointer. Okay, anyway. So for instance, you don't need to check all of them, right? So that means that you don't need to search for all over state space, but still this is a combinatorial problem, right? So this is for you to know. This is some of the motivations that actually came at the beginning from AI, right? When they were solving also planning problems. We will not discuss in general like a lot of these problems, but just for you to have a hint of other kind of problems that are solved in some cases, like with discrete planning. Okay, another good example, right? So this comes from dynamic systems. This comes from controls, if you want. Well, now RL is also using this as a benchmark method, but this is the inverted pendulum. The objective here is we have a mass. I want to forget about this. And we want to keep this thing up, right? So we know that this is unstable equilibrium state where any small perturbation is just going to pull down again the pendulum, right? So the stable equilibrium is you're just down, you're just looking down and you don't move. You need like high perturbations to move you from this state. On the other hand, when you are totally up, a little change is just going to create like momentum, and then, well, it's going to change your state. So how is this? Yes, how is this represented here? So what we are writing is kind of flow chart, right? So this is the discretized orientation and angle and angular velocity, right? And what we are looking for is this region that preserves these properties. So you see that the angle value is around pi, right? So this is what we are looking up here, like here, right? So this is around pi. That means that it's vertical, and we want zero velocity, right? If we go there with velocity, that means that we have swing more times. Now, how is this related to discrete planning? So on an extreme case, you could just be discretizing the dynamics here of the system, not dynamics, but well, let's say that we can create just another extra variable that is derivative of the state variable that is angle, right? We calculate all transitions. And then what we have is this kind of diagram. This is what is happening if we want to apply any action, right? In this case, action is a second derivative of angle, right? So we are applying this torque, and we want to achieve this equilibrium point here, right? So this is kind of the actions that we should be taking. We'll not get into this, but it's very interesting because planning actually is a very powerful technique. Why is that? Because you see, you start here. So this position, okay, maybe I'm going to use a different color. This position here, this is the pendulum looking down. And you see that there's not a direct line going here, right? Right. So you could be saying, what is the best thing that you can do if you are like with your pendulum looking down? Just put your action space directly pointing to this desired state. In this case, it's not possible because there's some maximum torque that you can apply. So that means that you need to accumulate energy, right? So in this case, planning what is giving you, okay, even though that you discretize the state and phase state, you have all transitions, you are still able to calculate what is the best way just to accumulate energy, like doing swings, until you get to the position up, right? So we'll not get into details. There's many ways of solving this, but I'm saying that a possible way is you can just do like broad discretization, and then well here, where to discretize. This is also kind of sensitive thing. And at the end, yes, we can consider this as a planning problem as well. This is just a hint. We will not treat like in-depth dynamics or stochastic processes for matter of noise. We will start talking about transition functions and noise. But the reason is because we are building here the building blocks, right? So I think it's easy to understand this problem if we start with discrete spaces, then later we add noise. You will see that for solving these problems, there's very powerful techniques like value iteration and other techniques that allows us to solve this from any state variable that we have. But if we start with dynamics, I think then there's more components that we want to discuss about. And that's why in this course, we will not talk much about dynamics. Okay, so it's there, it's an important component. At the end, anything real is kind of a dynamic system. But you will see that we just go to transition functions. I will define them in a couple of slides. Well, actually here. So let's discuss now that we've seen some examples of what a planning problem is. Maybe it's a good chance for you to, I don't know, ask something, or maybe think about another planning problem that maybe you have found like doing other courses. Sometimes they are not really called like planning, so it depends on what you are doing. But think about other problems that you have worked on that adjust to this kind of definition, right? Okay, so these are the ingredients that we need for all these planning problems. First one is we need a state space, right? Since we are working with discrete planning, what we'll need is a finite set, or at least if it's infinite, it should be countable, right? So examples of this could be, I don't know, maybe you have a problem that has integers. You will never get to super long integer, but still you need to take this into account. This is part of your state space. Continuous space are not really like part of this, right? So that's why we are discretizing into this finite set of states. We will note this as capital X. The other very important thing is that for each state X, we have an action space, right? And this is for every action space, for every state space. If you recall, yes, problem that we had before, right, where we had a grid, it will be something like this. Okay, I'm gonna do like a very small grid. I'm just gonna take, like, for instance, this xi, okay? And now I'm gonna define, so this belongs to this capital X, okay? So each of these points belong to the capital X. And now what I'm defining is the action space around this state is telling us like 3 actions, right? So you can go up, right, you can go down, you can go to the left. There's no up because there's no action that is gonna lead us like there, right? So this is because this space is limited. But yes, each of these points is gonna have its own action space. Okay, wait, we have a question. Didn't really get the idea of inverted pendulum planning problem. Is it related to how can reach on a state from another? Yes, exactly. So let me elaborate a little bit more on this. What we have is a large number of discrete spaces. So you can think about this graphic that I'm showing here as your state space, okay? Each of these pairs of angle and angular velocity is a state space. Okay, so according to the definition, we have a state space defined. We have an action space. And here, this is where, okay, maybe it's a little more complicated to see, but we could also be discretizing this action space, right? And this results in a new state. So let me just introduce the new transition function, right? So this is what is taking you from one to the other. What I'm saying is that there's a way for solving this. Probably it's not the best one, but you could define this problem as a gigantic grid. What you are looking for is from any starting position, you want to end up here. Okay, maybe I want red. Yes, red color. Okay, so this is our goal. Okay, and then you are starting from any point. And what you want to do is just to calculate the path for you to get there. So take a look that you cannot really do it. So I think you need to do something like this and then something like this. Right, so this is the analogy here. You have a very complicated thing. It's not straightforward. Straight lines are not going to help you because this is an underactuated system, right? You don't have enough energy. And the planning problem is, okay, so how can you actuate this system just to get to this desired position? Okay, so no, what I said is that angle and angular velocity are not discrete spaces, but if you see, So this is an image, right? An image is a set of pixels. There's a discretization happening here. You need to discretize your state space, and this is what is happening. So we are representing this discretization. This is not continuous. That's what I said, that you could also be solving this with more appropriate techniques, maybe solving them on continuous spaces or other kinds of discretization. So the point is, we have here a massive grid, okay? And from this massive grid, we know transitions, and we could be calculating paths. So this will be like one of these solutions, for instance, like this red path that is getting us to the desired or the goal state. Okay. This problem, by the way, it's a little more, I think, complex. The simple one to start thinking about is the maze. And we'll see in problem set 1 that what we have is a variant of this, right, of this maze, but we will add configuration space, and I will talk about this a little bit later. Why are we looking at non-optimal paths? Like control theory basically answer optimal paths. This is a good question. If you remember the piano problem, what I was telling at the beginning is that it's just so complicated to solve that sometimes you just want to solve it, okay? Once you solve it, we will discuss on many techniques to optimize these paths, right? But as a question to be answered by planning, sometimes it's not always optimality, right? Sometimes we just care about feasibility. So I agree, fine. If you have guarantees, you could be calculating your optimal path, but maybe you don't have these guarantees. Maybe you're on a higher dimensional space. Maybe you don't know where the obstacles are. There's many problems that could arise that, yes, on the best case, you want to be optimal, but we'll start with this. We start with, let's say, small objectives, and then we will increase from there. So I think from almost every of these problems, there's a way of defining optimality. Maybe it's not a global optima, but maybe you start just with some solution from a path, and then you optimize, or maybe you still can find like global optima, but still feasibility is for problems when you don't even know if you can solve. Okay, gotcha. So far we have defined these 3 components. Okay, all of them, I think, very important. Maybe some of you have already heard about transition functions. It's just this, right? So what you have is a state variable. You have an action. Remember, it's from this action space. And then you can think about this as a new state that results of executing this action. This new state, by the way, has to be inside the state space, right? If it results in another, then it will not be valid. So that's why we have a little problem sometimes on how we discretize and how we apply actions for dynamic systems, I mean. But in general, could be something as simple as, okay, you are just moving, yes, you are just moving here, right? And this is your new state. So this is your new state that also belongs to X, right? So very important. If it doesn't belong to X, then we need to define exactly like what the problem is, because maybe we need different discretization, or maybe we need a different transition function. Okay, another very important component is the initial state, right? We have also discussed about this. You always start at some point. Why? Well, because this is just given. Consider this kind of initial condition, right? You always start somewhere. This could be any point, by the way. So maybe you don't know where you are, but for your initial conditions, you just need to put like 1 point. And the final element is the goal set, right? So the goal set is not a unique state. It could be like a set of them. So why are we saying this? So imagine we are here, and then we define our goal state to be these 3 states. Why? Well, because, I don't know, maybe the region you want to get to is large enough. Maybe because of discretization errors. It's not really important, right? But usually what we have is a goal set. You could be defining just as a single element set, right? Without loss of generality, I think this is still okay. So you could have just 1 element if you want. But usually, yes, usually you have conditions that are a little bit larger. Now comes the interesting thing. So we have defined all these 5 elements. If all these conditions are met, then we have a problem that is well defined. Okay, yes. So what it means is that if we convert this problem into a graph, and then we apply a graph search algorithm, it's guaranteed to find a solution in finite time, if any, right? So this property is completeness. You can check out on Laval's book to know a little bit about this. So this comes directly from graph search. Again, planning, the only thing it's doing is translating this the planning problem into graph search. And once we have this, we will use all this powerful machinery that is behind. I'm sure that many of you have already studied some graph search algorithms. Popular ones are Dijkstra, A star, etc. But we'll give here some hint, right? So if we have these conditions, then the important thing is that we'll find a solution, right? And this is a very good guarantee. If there's no solution, then we will not find a solution, right? So then we can be sure about this. Okay, so as I said, this is I think the most important idea from today's lecture. So discrete planning becomes graph search. This is it. After having this discussion about different problems, how you discretize, maybe they're already discrete. At the end, what we get is that we can create our graph, right? It would be directed graph, right? And while we are searching over this, basically, this is also a way for us to kind of explore or find our solution, right? Okay, another important thing, right? That graph search is systematic. So, well, this was a property that I kind of said. So completeness gives you a solution, but it calculates infinite time whether or not a solution exists, right? So this is important because sometimes if you visited all your states and you don't find a solution, maybe you want to know if your solution is not feasible, right? So in this case, this is a very important. You don't want to have an infinite loop calculating solutions and not finding, and then hoping, oh no, we still need 1,000 more hours to calculate a solution. Maybe it's not, right? So this also gives us like this kind of guarantees. Again, these are just guarantees, right? So maybe you need like very large time just to get there to tell you that there's no solution, but at least it's very strong guarantee. You don't have this with sampling, by the way. Some methods also focus on improving efficiency. So you can imagine that if you need to go exhaustively over all state variables, then things can get a little slow, right? But it basically speeds up this search, right? We'll see later a little negative effect of doing this, but I think in general it pays off the advantages. Okay, now let's move forward to the, I think, most basic search algorithm, right? So this is just called forward search algorithm, right? It's based on a data structure that maybe some of you have already, well, you will have already worked on this and you already know, right? So these are just queues, right? It's a way of ordering kind of your set. We'll see like different strategies depending on the kind of queue. We'll have a different graph search algorithm. So this is also important. As we said before, the state transition graph is revealed after applying actions. So why is that? Imagine we're at the beginning. This is our graph. We only have the initial node. We only have the initial state, right? So this is a single node. We don't know anything else. Why is that? Well, because we haven't really explored, we haven't executed anything. And then these lines here, what they are doing is after selecting a vertex in this graph or a state variable, if you want, right? So now we are talking about these two things, planning and graph search. After choosing one state variable, we'll be just applying all the actions that are available there, right? And with this, the idea is that we can make our graphs grow, right? So with this, we will make it grow, and we'll see later like a little more particular examples of this, right? But this is. I think I need a pointer on this. Yeah, it's very small. Okay, anyway, so we make it grow, and this can give you a hint that we are going on the right direction, right? So we are exploring things, and we are just adding more elements into this data structure. The only downside of this is that this is only gonna give you output, a positive output in case of success, right? And in case of not success, because we have explored all state variables, then our data structure is empty. If we get to this situation, that means that we have failed. It's not possible to solve the solution, to solve the plan. This is the only output that this algorithm gets, right? So this is not very useful. So we do a lot of calculations. We go over these loops here, right here, and here, right, on these whiles. And then at the end, we don't calculate a path. So this is exactly not what we wanted, right? What we want is to calculate a solution. We'll see that there's a very small change that we can do just to keep track on patterns, right? And with this, basically, we can keep track of the path as we are doing it. But let's say that just to search for the full state space, this is the most straightforward and naive approach. You just, for all these variables, you just execute actions, and if they are new, right, if you have not visited them, you insert them here. So kind of easy. Just as a side note, get first is extracting one element from the queue, right? So you can think about this as you get whatever the queue is telling you, last one, first one, best cost. There's many differences here, but in this queue, this operation is removing, right? So here we remove X from queue, just in case that maybe, well, just a refreshment for this. Okay, very good, very good. Let's now get into some details. I will hope to do this correctly. I need to write a little. And I'm going to use, yes, a different. So let's start with breadth first, right? Breadth first is just a variant of the forward search that I was talking before. But the difference is we'll have a plan. We'll have a plan solution as output. So this is great. This is what we want, right? And the other difference is that now we are defining our queue as a FIFO queue, right? So this is first in, first out. First elements that get in will be the first later to get out, right? This again is just changing the output. So we will get flag telling us like, yes, you succeed, or no, you failed. And then you also have a plan, right? Because we can keep track of this. And the way of doing this is with a parent table, right? So because the graph structure that we generate like this is a tree, you will see this in a moment, right? I'm just going to do an example over this. But because we have this, you just need to traverse the tree, right? So you just need to get back. Every node in a tree, for those that maybe one little reminder, only has one parent. So this is a great property for trees. And then the only thing you need to do is just get back, right? Ask every vertex who is their parent, and then you solve the plan. Okay, I want to come here, try to see nodes in case I do something incorrectly, but you can also do this. So if you have a piece of paper next to you, and if you have, or maybe some notes, you can create this. So let's now visualize how the queue looks like, okay? So I'm going to start with the first point here. That is this one, right? So our queue at this point is telling us that X0 is the only state. Okay, why is this? Because this is our initial state. Here you see. Okay. Here we see this red. This is our initial state. Right, I'm gonna write it as 605. And then the algorithm is just doing this. If we started with an empty queue, then that will be like the end of the algorithm, right? Because then we'll be here. Okay, so we start here. And now let's start with the first iteration, right? So we are at iteration number 1. We are here. We get our first element, right? So we are here. Our X, now there's only one element in the queue, right? Maybe for some of you, I'm going like very slowly, but I think this is okay. I want everyone now to have like this very simple example, right? And then later when we ask you to do problem set 1, which is going to be related to this, I think on when you implement things, things will be a little more, you will have like no doubt when you are implementing things. Okay, which one is xg? So in this case, xg is going to be x4. I mean, in this kind of example, and then here what we have is x1. Okay, so what we want is to get here. Okay, so let's go in order on this algorithm and see exactly what's happening, right? So we get this component, fine. Is this your goal? Not really, right? We're still a little far away. Now what we do is for all the actions available, we are just gonna do transition function, right? So for instance, first action that we can do maybe is this, right? So we go to the right. We don't know exactly what this action is, but this is just for the example. And then there's a second action that is, okay, we have this, right? So on one of the iterations will be like this. We'll mark X as visited, right? So X1 and X2 are going to be visited after doing this, and then we will insert them into the table. And this is what we were looking for now here, right? So we'll have our new queue that, remember, now it's empty because we have removed X0. We are going to add first X1 because, I don't know, maybe this is how we were defining the order on actions. Actually, this is a very important thing also. When we have not a distinguishable way of ordering actions, sometimes this will result in equivalent plans or in successful plans that are not exactly the same, right? So imagine that now instead of putting first action going to the right, it's on the left, right? So this will change the solution, maybe on some cases. Okay, so this is for first action, and then for second action, we have a queue that is just 2. Okay, so goal state vector. Now, in this case, okay, so you were answering to this question about what is xg. Yes, yes. In this case, what we have is a set that consists only on the x4 element. Okay, so here we are not adding more elements into this set of state variable for goal. It's just like one, just to make the example easy. Okay, so that's it. We are now worrying only about Q, right? And let's do the same, right? So let me ask you here. If we have this kind of setting, FIFO-Q, which is going to be the next X that we choose? Anyone? Yes, thank you. So we have X1 and X2. And because this is a FIFO-Q, you, yes, you will get X1. So X1 is our new selected state. Oh, X1 is here. Yes. So this is where we are. Iteration 2. Okay. Certainty. No. These are all deterministic transitions. So for now, we will start with discrete spaces and deterministic transition functions and deterministic state variables, right? So there's no observability, there's no latent space. Here, what we see is what it is, right? So this is later, you can add more things. We'll do this later. But to start, we will start with simple, most straightforward and the most important thing, which is, okay, now how to traverse the space and what is the action, what is the goal, states, etc., etc. Okay, so we come here and we do the same, right? Remember that now we only have one action. So in this case, X1 only accepts one action, that is going to X3. So that means that our new queue, remember that X1 has been removed, right? So I'm just going to remove it. So what we have now is X2, and then this is the new one. This is the new state we are adding, right? So remember, we are adding this at the end of the queue, and well, this is going to be our first state. Okay, so you got the idea, right? Let's keep doing this. I equals 3, right? So our new X is just going to be X2. So we get back here again. And here we have kind of the same problem, right? So our new Q, our new data structure, it's gonna contain X3, right? So we have removed X2, and we are adding this new that is X4. Okay, so we are almost there. Let me see again. We are at X4. X, unfortunately, is gonna be this one, right? So first in, first out. That's why we call this breadth first, right? So if you want just a way for you to remember about this, is that we are going on breadth. So we are exploring kind of the same level of inception into the graph. We're exploring this exhaustively. So we add one, we added first this one, then we added this one. So what we are doing is on our queue, we are just getting, we are just propagating each of these states, right? So systematically. We'll see a variant of this, and it's just a very minor thing. Wait, we have a question. If fxu, in this case, is a list of possible actions where we can move. Yes, yes, when your transition is not exactly, so why do you want to have like multiple outputs as you, I mean, that your transition function is outputting different state variables. So sometimes what you have is this discretization problem where you cannot have like a unique exact state variable from your state, but sometimes the solution is kind of combination of several of them, like some sort of well, yes, linear combination, or maybe you have a stochastic process here, in which case you have multiple of them. If you have this, then probably you don't want to use this kind of technique. You don't want to use graph search. So graph search is well defined when you have a transition that is telling you an action that is defining your transition as a single element of your state space. If you have multiple, we'll explore in lecture 4 more powerful techniques for doing this, which are mostly dynamic programming, and well, just a concrete case could be like value iteration, right? So on here, you can consider like these multiple cases where your transition is giving you more than one state, right? But here, what we have is you apply an action, you get one state. There's no distribution of states, right, at the output. Is that clear? Is that what you were asking? Maybe. Yes. Okay. Yes. It's a good question, right? Because but usually you need to think about them as kind of perturbations of your transition or uncertainty in some way. For now, let's start just with deterministic cases. With this, we can have this kind of graph search algorithms. If not, as I was saying, then the magic is not there. We cannot use graph search, and this is sometimes bad news because graph search is very powerful, but it requires you to have the exact list of components, right? So if you don't have this exact list of components, it's okay, but we'll need to think about other techniques. Okay, good question. Let's get now to let's finish kind of mental algorithm. We are here, our x is x3, right? So here we're analyzing this thing. And then we have an interesting problem, right? Because we have a queue that is already x4, right? We have removed x3. And then according to this, it should be telling us to add a new state variable, right? So this is why we have this case here. So we need to resolve duplicates. We cannot add into the queue 2 times the same thing. This, by the way, was a problem that we faced, that students faced last year. So they were not handling duplicates properly. They got a solution working, but only after looking like 1,000 times more, traversing 1,000 times more nodes than it was required, right? So then they were, oh, my solution is very slow. How is that? This algorithm is not very good, right? And then we were looking at number of times, and they were not solving duplicates, right? So this is just for you to know. We'll show later like a way of solving duplicates, but do you know what is the simplest one? Let's ignore this, right? Let's ignore this guy. He just got late. We don't care. So, no, you don't agree? Okay. It's okay. So this one just gets like ignored. And then it's a bad way of solving duplicates. What are number of edges? So edges will be the number of times you execute your transition function. You don't really need to take this into account. No, actually, no. Those edges are these minus all those that were already visited, right? So it's probably a little bit less. Okay, let me then reread the question because I think, what are the number of edges? I mean, number 1 and number 2 on each edge. Yes. Yes, this is a directed graph, by the way. So that's what I'm not getting back again to x0. But if it was in directed graph, then what we should be doing is, no, there's no cost for now. Cost is, can you do it or not? You see that there's like little cost here, but this algorithm is not taking into account cost. It's just looking if you get to the goal or not. So edges here on x1, it's only 1. It's only going to x3 because this is not, there's no edge here. So let's think about this as directed graph. And the same happens for x2, right? So they don't go back to x0. But if they were going back to x0, then what we'll have here is a loop, right? So inside, tree will be growing enormously, right? So you can still solve it. And maybe this is an example of, yes, like why we want to keep track of visited nodes, right? But if you get back, no, actually, no, that's not true. No, you will just solve the duplicate, right? So it's a node that you have already visited. Algorithm will not have like a great overhead, right? Because it's already visited. So you will not be coming here adding more nodes into the queue. It's just going to be the same. So in this case, it doesn't really matter. But for this example, this is a directed graph. Okay. Okay. Let me now finish finally. I'm very slow. I hope that your algorithm is a little bit faster if you want to pass problems at 1. I'm sure it will be. Okay, so we get to 5th iteration. Our queue consists only in 1 element, right? We have x4. And then what we have is that simply instead of executing the action space that is around this node, what we do is we come here and we check for this condition, right? Is your new x part of this x goal? And the answer is yes, it is. Okay, so with this, we return success. Okay, very good, very good. Again, I'm just putting things in slow motion. This is just an example for all of you to follow. So maybe it's kind of trivial, but don't worry because we will add elements just by showing, right? So explaining these algorithms usually is like very abstract. So I didn't want just to put the algorithm and moving away. So that's where we are doing this little exercise. If you find this easy, I'm gonna do a break now. And what you can do is calculate in advance the parent table. Okay, so we'll be following the same kind of conditions, and you can calculate the parent table in the meanwhile. We'll be doing this, by the way, for a depth first algorithm. Okay, don't worry. What I mean is that you could be doing things in advance and then check if we are doing the right decision. Let's do little 5-minute break, and at 59 we'll be back. Okay.
Professor, can I ask you a question?
Yes.
Professor, I would like you justify the purpose of the parent table, because I don't understand the notation. As I understand here, what is said, parent table is the path that we are followed up to the current state. And in the current state that we want to calculate, we are try to memorize the verge, it calls, right? The verge of the graph. We try to memorize the verge of the graph, and we put it inside parent table.
Mm-hmm.
Yes or no? Because I don't understand the purpose of it. Parent table.
Yes. We'll give an example now, right? But you will see that this is the missing ingredient for you to calculate a path. So what it happens is that then you just need to backtrace from your goal state. You just need to backtrace on your parent table, and then you will find a solution. So that's why you need to keep this thing in memory. Don't worry, in 2 minutes we'll do like the example. If you if you don't have this, you don't have a way to know how you get here, right? So now what we have is all these cues, but they are not telling us how we got here. So this is what we want to know, and the best way is to memorize, like how we got here. So this is a little bit the motivation behind. Okay. Yes. Oh no. Ah. Okay, okay. Let's get back. Let's get back. Um, so maybe some of you on this break just had a glass of water, but maybe others try to redo this queue. Now let's do a little different example. And I think this can be also a good chance for us to present the other very famous forward search, which is depth first, right? The only difference with respect to the previous slide is this one. We are changing the queue to be a last in, first out, right? This is the only difference, and this totally changes the behavior that we are gonna get, right? And as I said, now we are gonna track this parent table, right? So that means that we'll have all our state variables, right? And in this parent table, we want to write who are their parents, right? So for now, none of them have parent. The only thing that we have is that, if you remember, this is the queue at the beginning, right? So we only have the initial position, okay? So let's focus now on what is the, how this parent table looks like. Okay. Okay, I'm gonna go a little faster, but I recommend you that you either follow what I write and then you try to make it sense, or you try to do this faster than me, right? Okay, so we are here at the first iteration. Okay, so what we know is that at the first iteration, we are gonna get x equals x0, right? So we get our queue empty, we have this state, and now because this is not goal, what we need to execute is the two actions, right? And in this case, what we have is these two variants, right? So first one, we can get to x1, and the second we can get to x2. Okay, so previously what we did is this, we added, how I was adding this? Yes, let's say that first we do x1, just to be sure we were doing the same. So we start with an action. Let's say our set of actions is ordered this way, that x1 is the first one, and then we have x2, right? So far, no difference from before. The interesting thing is that now what we have is two parents, right? So this is calculated here. When we come into this iteration over the current state, and then we iterate over the possible actions we can get, we know that the parent table is going to be filled in, right? So this is what we just go there and say, look, you all guys come from x0. Okay. Let's go to the next iteration. Okay. What we have is that this is last in, first out, right? So last in, first we put x1, second we put x2. So that means that we are choosing now x2. Okay. So this is the first difference that we find between depth first and breadth first, sorry, that we explored before, and depth first that we're exploring now. If we come here to x2, we only have one possible action, right? And this action is telling us to go here to x4. So it means that our new queue is going to look like this. We have x1, and then we add here x4, okay? And the good news is that for x4, what we have is its parent, x2, okay? And now the next iteration, what we are going to be doing is the same. We calculate what is the current x, and this equals goal, right? So then we are finished. Now here comes the interesting part. Maybe let me find orange, right? How can we use this parent table? This is what I was discussing before in the break. We are here, okay? So this is our goal state. We always want, I mean, if there's a path, there's a feasible path, our goal state should have a parent, okay? If they don't have a parent, that means that we cannot do anything because we didn't reach this state variable. So if we didn't reach it, there's no path. So there's always one. So what we are doing is just look up, okay, from X4 that we are here, the parent table is telling us to come here, okay? So this is the parent. Now we come. And then we do the same thing here, right? So we just update our new variable, and then we want to find out who is the parent for this, right? And it's 60, right? So you need to imagine this as a tree, and we are just traversing the tree, right? So it's very, very trivial, but this idea should be like well understood, right? So I'm sure that most of you already, oh, okay, I already know this, then awesome. But this is gonna be the fastest solution for you to calculate path. Another interesting thing is that because of this LIFO queue, we don't know the parent of X3. We simply don't know. We never reached it. We never executed actions or calculated transitions from this. So that means that we don't have any clue of who is this guy. So that doesn't really matter much. But maybe if we are looking for optimality, this kind of condition is not really the best, right? So we'll see later that actually if we want to ensure optimality, we need to, well, be a little more smart on how we are choosing the elements. And well, this is the next kind of graph search algorithm. It's no longer, well, yes, it's kind of a version of forward search, but Dijkstra algorithm is a little bit special because now what we are doing is calculating the optimal path, right? So this is done almost at no cost, right? It simply needs to change a little bit how we are doing the queues and how we are defining cost. So the first change with respect to the previous two approaches, breadth and depth first, is that our queue has changed. Now is a priority queue, right? So a priority queue, what it does is it keeps track of, it basically has pairs of elements, one of them being our state variable, and the other being a real value. In this case, real value or any other element, right? We'll choose just a value because this is usually what helps us to keep cost, right? So we just define cost as real value, real values, and that's what kind of a standard. And then the other thing we need is to define on this graph some cost, right? So for traversing each of these edges, so that means executing actions, right? We have this cost, right? So some of them have cost 1, others have cost 2. We don't know why, but well, this is part of the graph. And now the problem is, okay, let's execute this. Let's execute this algorithm because, well, it's a little bit different. And in this case, what I'm going to focus now is on the priority queue again, but just including cost, right? So this is the new important thing. Our initial element here, right? So we have x1, no, x0, sorry, and cost is 0, right? So this is what is put here, right? So initial cost is 0. We could be starting with any cost, doesn't really matter, right? And then we don't have any definition of cost anywhere because we haven't really traversed them. So you could not initialize them, or you could use any other value. That's a little up to you, right? But what is gonna help us is not really what is the current cost, but actually if we have traversed this node or not, right? Okay, so let's do this again. Now, the problem is for those that want to do next to me is I'm just gonna go iteration by iteration. And I want to calculate what is the cost, right? We want to solve this problem, but I want to calculate what is the cost. So this part should be already familiar for almost all of you. We only have one element. We have previous cost. And remember, here, what we have is two new elements, right? So let's say that first we add x1, and the cost for x1 is 1. See? And we have another element in this priority queue that is x2. And note that I'm not really ordering them, right? So just because they have the same value, so that depends a little bit on how they are implemented. But if they had a different value, like for instance, this plus, right? Wait, I'm not sure. I'm not sure if they are ordered like from bigger to lower or lower to bigger. Okay, let's say that we have here a little bit value here, like a plus, and then here, this is what our priority queue is telling us, right? So we have this element here, we have this element here, and well, now that they are the same, it doesn't matter, but we'll see another example with this matters, okay? So let's say that, yes, this is a plus plus. So this is 0.1.0 something, right? So that means that when we come to the next iteration, we are going to choose the minimum one, that is x2. Okay, so x2 will be doing exactly the same thing, right? We are going to be calculating, well, first of all, this is x1, if you want. And then we are going to have the next element, right? So for x2, next element is x4, right? This is great. And now let's put here the cost, right? So the cost is the cost of x2 plus the kind of edge cost between 2 and 4, right? So this is what it is. So before, the cost at x2 was 1, right? And the cost of traversing this is 2. Okay, so very simple example, but this will clarify things. So in total, what we have is 3. So in our priority queue, let me order it again. It's going to look something like this. So we'll have x1 is plus, we'll have, yeah. So we were saying that we are going to take this from the left. So that means that x4 is going to be now here. So the priority queue is just changing the order, right? And then what we have is this. Okay, so let's move on. Next iteration. X is going to be x1, right? So here we just take minimum cost. We need to do the same thing again, right? So in this case, for x1, there's only one new variable that we can add. And the new cost, the new priority queue is going to look like this. So here we'll have 3. I'm just adding the same element. And we'll have this new element that is x3. And what we need to do is calculate the previous cost, that was 1, plus the edge, right? So 1 plus 1 is 2. Okay, so things look good. We have reached the final goal, but we'll see that it's not exactly as easy, because here at this iteration, we are not choosing x4. So see, x4 is not the best thing that the priority queue is telling us. The priority queue is that it's telling you, look, you are looking for the best next pair of elements, go to x3, right? So here, this is what we are doing. And then with x3, what we are doing is calculating the same thing again, right? So here we are going to have x4, 3, right? And then what we find is that actually we have duplicate, right? Because the other element that we'll be adding is also x4, but in this case coming from here. And the cost for this is 2. So this is what cost values here, right? Is 2 plus 2. So this will be 4, right? And in this case, this is how we solve the duplicate, right? So here, what we need is to solve this duplicate, right, between these two. And a way of doing this is, okay, so you want to look for minimum cost, just take whoever is minimum, okay? Take whoever is minimum and think about this, that it's not just removing your priority queue, but it's also taking care of the parent table, right? So if in your parent table there was a different value, then things should be updated as well. Okay, and that's it. So now what we have is a queue with only one element, and this element is x4, right, at equals 3. So this is the best thing we can do. Come here and come here. Okay, so if you haven't, please try this later, right? So everything that I'm telling you is just by induction. You can solve it. Numbers you can make up, or you can just repeat the same experiment. But this, I think, is required before you start implementing things. Okay, let's talk now about a very, very popular technique that is A star, written like this, pronounced A star. This is a very old technique, by the way. So this was created almost 60 years ago. Well, it was originally done for Shaky Robot, I think, but anyway, yes, this happened around the 60s, and the thing is, so they were optimizing robot kind of navigation. Okay, so the principle is the same. Here we have the same kind of priority queue. We need to define a cost function. We start the same, but if you have noticed, one property of Dijkstra is that this is exhaustive, right? No matter what, it's going to find out all cost that is required to check, right? So there's no way for you to speed up things. If there's like a cost that is a little slower, even if you know that this solution is never going to be executed, it's gonna check it, right? So this gives you like good guarantees because the solution is going to be optimal. But depending on what is your problem, maybe this is not what you want, right? So A star came as a solution for this. They are proposing basically like two cost functions. One is traversing a graph, or cost associating to each of these edges. So this is the same as Dijkstra, but there's a new cost function that this one is very interesting, right? And actually it's debate, it's topic for debate. We have an heuristic function. This is an estimation of your cost to go, right? So for instance, you don't know what it takes for you to go to the goal, but maybe, oh, sorry, let me write this. But maybe what you have is a good idea of what's going to happen, right? Like for instance, you roughly know how far away you are from your goal, right? And usually metrics that are used here are L1 norm, right? So imagine you are here, you are in this current X, and then your H function between these two could be like something like this, right? So L1 would be like this, but L2, sorry, but L1, what it's doing is this kind of Manhattan distance, right? Okay, let me try it like this way. This plus this, right? So it's kind of a square. So it's looking down and then to the right. You can do this for grid spaces, two-dimensional grid spaces, maybe for 3D. For other things, it's not so straightforward, but still, this is an estimate. And why is this so interesting? Because, as I said, this is part of the problems on estimating and heuristics. It's guaranteeing an optimal path if this heuristic is underestimating this cost to go distance, right? So maybe later here there's I don't know, an obstacle, and the cost is not going to be this, but this, right? So it's going to be more than this, right? So in this case, you're underestimating what is the real path that it's going to take. If that's true, then you will find optimal paths, right? Because this is kind of the situation where you still gonna take them into account. If you are in the opposite side, if you overestimate like what is the cost and think, no, yeah, this should be like more, and then you don't explore these things, then you are not guaranteed to find optimal cost. So that's why defining this heuristic is so tricky, right? So for the classical example on 2D, it's easy. If you move to higher dimensional spaces and other problems, same as what we'll be doing in problem set 1, then defining this heuristic function is not so easy. Okay, what else? Yes, so this is what I just said. And in 2D, yes, it's kind of straightforward. L02, also known as Manhattan distance. What is the difference between Dijkstra and A star? So these are elements that were present in Dijkstra also. The only new element is this one. So what we have is that every time that we are adding a new cost function, instead of adding the cost function, is that plus the heuristic, right? So this heuristic that is telling you like estimated cost to go is just going to help you how you order the next nodes. And you can imagine that the way you are choosing them is very important. So ideally, you want to choose like only those that are relevant. And if that's not possible, you want to check as few as possible. So this is just going to give you a way of ordering them a little bit better. Wait a second. We have a question. In case of duplicates, else part, why we don't add to the priority queue again? I think the optimized cost may optimize other nodes as well. So if you add to your priority queue a duplicated element, this is going to be bad, because then how the queue works is that it's going to remove one element, right? And then you are going to analyze it, whatever the cost is. And then you are going to, when you come again, extracting elements of your queue, you are going to extract this element again. And this element has already been studied. So you don't want to do this 2 times. It's waste of time. So once you have your X, wait a second. Yes, once you get this X, you don't want duplicates. If you do this, then you might just be not as efficient as you think. So this is not affecting optimality, by the way, because if you handle duplicates correctly, which is with this formula, you already have like which one is of minimum cost, and then you kill all the other things. So just by improving your parent table, changing it in case if there's like a change, and changing the cost will allow you not to process things more than required. Yes. The same happens here in A star. So you could be handling duplicates just by leaving them, and then you are just going to grow and you are going to do more checkings. And well, this creates a lot of problems because actually, yes, you start with a different cost that is going to be a little bit more. So yes, no, you don't want that. So look for duplicates, important part. Okay, and what else? Yes, I think now we are ready to kind of announce what is problem set 1. I already said, maybe no surprise, but it's going to be application of A star. It's not going to be a straightforward problem, so this is not a 2-dimensional grid map, but basically it's a 2-dimension with an extra dimension that is orientation. So for this, you'll have to wait a little bit for next lecture, right, where I'm going to talk about configuration space, right? So what we'll be doing is formulate the problem of position of a rod and its orientation as a discrete problem, and then just apply A star algorithm, right? So it's not as just finding the path, looking for L1 norm. So this is kind of very basic. This is a little bit more because you will see like in more detail. So you have here higher dimensional space, other things. And well, let's say that, yes, it's more interesting. If you want to find out about, you can start taking a look at the problem set. It's already pushed to repo and to Canvas. Yes, so there you will, I mean, the initial questions are visualization and very simple things. So maybe you can start taking a look. I will try to upload the slides for next class as soon as possible. So that way, if someone wants to start working on this, I think you have already tools to solve it. But there's only this little issue on configuration space that we haven't really discussed much, right? So if you want just to wait for next Monday, and then we will explain things properly on configuration space, that's also okay. Great. So it's also actually very fun. So you will see your little rod moving or colliding, depends on your algorithm. And then, well, the solution is kind of rewarding because you will see the thing moving, and this is also always fun to see. Let's talk a little bit about some considerations, right, about choosing good heuristics. So if we find the right heuristics, and this can be like a topic for research, then you can speed up things a lot, right? So there's like, for instance, papers that consider position and velocity. So you have four-dimensional spaces, position and orientation, plus velocities if you want. All these things basically are problematic because of the course of dimensionality we commented before. But if you have a good heuristics, maybe the dimension is not such a problem, right? So there was like a lot of research in 2000s, right, about this, about heuristics, many things, right? And they came up with very good solutions. It's not trivial though. So for moving things on a chessboard, yes, it's clear, but if not, it requires tuning, and still solution can be damaged. Yes, this is the last thing. If you become too greedy on the choosing of heuristic, if it's not underestimating your state, then you will get a solution that is not optimal. So there's no way for A star to undo these things, right? The extreme case of underestimating is everything is zero. And if everything is zero, then what you have is Dijkstra, right? The other case, so you have like very biased solution, right? Like trying just to go to direct to the goal and then getting into some kind of detours and other artifacts, okay? So this is a discussion that we are just presenting briefly. Actually, this topic is a little more deep than what I'm just presenting today. So remember, we will start introducing topics gradually. So we start with this, some of the problems, but in lecture 5, we'll talk a little bit more about this, right? About cost to come, cost to go, and dynamic programming is actually considering this like properly. Okay, what else? There's another very interesting variant of this, probably it's just enough for you to know, that is backward search. This case is a little bit different because we start with goal and then we move backwards, right? And the only difference is here. Now what we have is this inverse of your action space, right? So what you want to define is all these state variables that are valid on this transition function, right? So you see that this thing becomes a little more complicated. This inverse function, actually, it's not an action. This inverse state space, sorry, is not, no, inverse action space is not just an action, it's a pair of state and action, right? So that's what I'm writing here. And then whatever takes you to the current state, so that's the definition of inverse, you put it this way, and then all the other machinery that we have discussed is the same, right? Why you want to do this? We'll see an example, but maybe some problems require, I don't know. For instance, you have an initial state that is very easy. It's on the field, there's not many obstacles, this configuration is very easy for you to reach. But your goal state is something very complicated, like imagine. So you start with your hand like this, totally open and no, or any position, right? And you want to end up your planning with all joints in your state variables to be holding a pen, right? So this is very precise kind of movement. Okay, I'm not even talking about how to discretize like joint position of your fingers. So imagine this is really high dimensional state. But sometimes what I mean is that the goal state is more complicated than the initial state. So what we do is you can change the algorithm, and maybe from this very complicated state, you can search and then get easier to a solution. The other reason is bidirectional search. So this is a very clever trick that we can do. And basically it consists on divide and conquer strategy, right? So what we have here is initial state. We have here a goal state. And what we are doing is we are just traversing, right? So we are just traversing the graph. We start like this, maybe we come here. And then eventually we change, okay? We start changing our solution, and then forward search is stopped for some time, and then we start doing backward search, right? So why are we doing this? Because if we alternate these two problems, then the solution at the end, it's only gonna be finding kind of connection between the two graphs, right? So that means that we are here, we continue doing this, we continue doing this. I don't know, maybe from here we get here. And then, yeah, here we have a duplicate. What do we do? Okay, so maybe this is not good. We came here, and then this is the graph, right? So this is like the connection between the two graphs. So imagine maybe two very complicated configurations, state variables, xi and xg. You don't really want to start from one and then going to the other, because chances are very small that you are going to find this state. But maybe just starting and ending and creating trees from there, it's a more efficient way of solving the problem. Is it happening at the same time? This is a question. Well, by happening at the same time, if you mean concurrency, you can do it, but I was thinking more on sequential. Yes, I was thinking on sequential approach, right? So you first develop one branch, then you change to the other, you change to the other, and you have kind of a main thread that is choosing between forward search and backward search. I think you can do this with threads, or let's say different processes. But yes, at some point, I think you need to sync both processes to find connections, right? So it's not so trivial to do it. Concurrency could be an interesting final project, by the way. Maybe if you're like into well, this kind of problems, but I didn't check on this like a lot. But my guess is that yes, concurrency is possible, but it requires checking for when trees connect, like on a process that simply halts, or at least yes, does not allow anything. Well, yeah, does not allow the trees to change, right, while you are checking. Yep. Okay. Another interesting approach of not just the bidirectional one is what is called anytime algorithms, right? So anytime algorithms are in general those that admit kind of incremental solution, and they could be refined over time, right? So this is important because now what you have is maybe some budget, you have some number of samples or iterations, and you just want to find a solution with this budget. So what this is giving you is that maybe you don't want to find the optimal solution, but if you find a solution and then you improve over this a little bit, this is good enough for you, right? So you first play very aggressively with heuristics, right? And then the remaining time is just used to improve this solution, right? So maybe you will need more samples than originally for calculating the optimal path. But depending on the problem, this could help you. And the good thing is that you will have guarantees that you have a solution, right? So imagine you want to find a solution in less than 1 second. So anytime algorithms could help you. There's like some publications on this, like ARA or others, that basically what they are doing is monotonically decreasing the contribution of the heuristic function. So they start like totally underestimating things like, okay, yes, let's go like this way. And then they just relax these things until they get to original contribution, right? There is one, like what is the original heuristics. And with this, well, I think for some problems, this kind of works very well. So you can see here an example. This was taken from this paper. And well, this was like a very popular research during, as I said, even 2000s. Now things have changed a little bit. So still A star, Dijkstra, and all these algorithms are widely used. So I'm sure that you've heard about them. And because they are so powerful, this is the only thing we are doing on discrete planning. We are taking them, and if it's possible to apply them, we do, right? So if we have a good tool, why not use it, right? So if there's problems, we can always find other tools. But the first kind of lecture that we did on this was more related to graph search. And I think it's more like, yes, like, okay, we have this great tool. Now, how can we adapt this to planning? I hope that this lecture answered this question. You will practice anyway in problem set 1. And now maybe some comments or some questions before we stop here. Okay, well, if not, thanks everyone.